Part 4. Impact of succussive dilutions. Outline of lecture. Explanation of impact of repetitive succussive dilutions on water, its solutions and other liquids. The next slides visualize within the context of QED the impact of succussions on liquids. Impact of succussions. Liquid containing domains. The information presented in this slide holds for all QED domain types described earlier in this lecture, that is CD-ROT, CD-IPDS plasma and CD-elec. Succussions cause turbulence and formation of whirlpools. By turbulence induced strong shearing forces tear up domains. The next slide visualizes an important difference between the broken pieces of the various types of QED domains. Succussing very dilute solutions. Liquid containing CD-ROT. Earlier it was shown that according to QED theory, for polar liquids, that is, liquids composed of molecules with an electric dipole moment, part of the molecules organize in CD-ROT domains. Moreover, even on addition of few solute particles, these solute particles, together with some polar liquid molecules, organize in CD-ROT. Within these domains, the electric dipole moments of the molecules are aligned. On succussing these liquids, the CD-ROT may partly break up. Immediately on breakup, the electric dipole moments of the liquid molecules are still aligned. Therefore, broken CD-ROT pieces have a net electric dipole moment. In the rest of this slideshow, broken domains with an electric dipole moment are denoted electric dipole aggregates, EDA. Succussing very dilute solutions creates electric dipole aggregates, EDA. Succussions, liquid containing EDA, SSEDA, SEDA. Whenever it will be necessary to differentiate between EDA containing solvent and solute molecules versus EDA containing solvent molecules only, the former will be denoted SSEDA and the latter SEDA. Electrolyte solution, concentration smaller than approximately 10 to the minus 4 molar. Earlier it was shown that in very dilute electrolyte solutions, that is a concentration smaller than approximately 10 to the minus 4 molar, ions organize in IPD-S plasma domains. Due to spherical symmetric alignment of the electric dipole moments of water molecules around ions in IPD-S plasma, these domains have no net electric dipole moment. Dipoles of molecules pointing in opposite directions cancel each other's forces. Spherical symmetric aligned dipoles fully cancel all dipole forces. Consequently, a domain with all electric dipole moments spherical symmetric aligned does not have a net electric dipole moment. However, after a succussion-induced breakup of an IPD-S plasma, there is no longer a fully spherical symmetric alignment of the electric dipole moments of the water molecules. As a result, most broken IPD-S plasma pieces will have a net electric dipole moment. Succussions result in SSEDA and SEDA. As to CD-elec, succussions do break up these domains. However, Within CD-elect, electric dipoles of water molecules are oriented randomly. Therefore, broken CD-elect pieces do not have an electric dipole. That is, succussion-induced breakup of CD-elect do not create EDA. Electrolyte solution with concentrations greater than approximately 10 to the minus 4 molar. No alignment of electric dipole moments of solvent molecules. As mentioned earlier, for non-dilute electrolyte solutions, that is concentration greater than approximately 10 to the minus 4 molar, solvent molecules do not organize into domains where their electric dipole moments are aligned. Therefore, on succussing such solutions, no EDA form. Succussions, no EDA formation. The next slide details some characteristics of the internal structure of EDA. Structural characteristics of EDA. Due to quantum physical effects, the internal structure of a CD rod has holistic characteristics. That is, its structure is a function of all its solute and solvent molecules. Consequently, immediately after a succussion-induced breakup of a CD rod, the internal structure of all its broken pieces, S-EDA, SS-EDA, is a function of the properties of its solute and solvent molecules. This point is important to remember. The above noted term, immediately after a succussion-induced breakup, refers to a very tiny bit of a second, that is less than a picosecond, 10 to the minus 12 second, after breakup of a CD rod. In other words, immediately after breakup of a CD rod, also the structure of broken pieces composed of solvent molecules only, SEDA, is a function of the solute molecules which are present in the original CD rod. This is important to remember. All the above also holds for an IPD-S plasma and its succussion-induced broken pieces, that is, its SEDA and SSEDA. An SEDA has a solute reminiscent structure. The next slide details the impact of succussion-induced whirlpools on the structure of EDA. Impact of succussions-induced whirlpools on structure of EDA. Immediately on a succussion-induced formation of EDA, whirlpools suck in the EDA. Within a whirlpool, EDA get rotationally excited. Though in a whirlpool an EDA continuously rotates, this motion is not shown all the time in this slideshow. Due to the EDA's rotational movement, its original structure is preserved. This is a central point to be remembered. The preservation of the structure of a rotational moving object results from the physical law of conservation of angular momentum. A typical example is a rotating open can filled with water. During its rotational motion, the water remains in the can. During succussions, an SEDA preserves its solute reminiscent structure. The next slide pictures the fate of EDA during the intermezzo in between succussions and after the succussions are stopped. After a succussion, due to the EDA's electric dipole moment, EDA attract other EDA. As noted earlier, EDAs are aggregates composed mostly of polar solvent particles. Due to the non-random orientation of the electric dipole moments of these polar particles, the aggregates have a net electric dipole moment, which causes them to group into a superaggregate. A superaggregate is mainly an aggregation of polar particles. With a non-random orientation of their electric dipole moments. That is, the superaggregate has an electric dipole moment. Therefore, a superaggregate is just a large EDA. The foregoing shows that after a succussion, EDA grow. After a succussion, EDA grow. Aggregation of EDA is a slow process which depends on the size of the EDA, starts immediately after succussion stop, continues during macroscopic times, for example minutes, months, years. Also due to the EDA's electric dipole moment, EDA attract polar solvent molecules. An EDA, together with its adsorbent solvent molecules, actually just is an enlarged EDA. That is, an EDA's attraction of polar solvent molecules also leads to its growth. Due to energetic and dynamic properties of liquids and EDA, not all polar molecules will ultimately join an EDA. The maximum size of an EDA is always less than that of its mother domains. For example, for EDA created from IPD plasma, their diameter typically is of less than a micron, for example opened 1 or opened 0.1 micron. In time interval between succussions and after succussion stop, EDA grow. The next slide details a characteristic of enlarged EDA. Enlarged EDA, adsorption of solvent molecules on the surface of EDA. Adsorption of solvent molecules on the surface of EDA seemingly is a liquid phase homoepitaxial process. Such a process occurs in liquids containing substrates with the same chemical composition as the liquid. In such liquids, adsorption of solvent and solute molecules on the substrate generates adsorption layers with a structure identical to that of the substrate. In other words, the adsorption dynamics is monopolized by the interactions between the particles constituting the aggregates. Thus, the particle aggregate substrates, by serving as templates inducing specific adsorption layer structures, transmit their structural information through their surface, hence epi, to the adsorption layers. Due to epitaxial adsorption of liquid molecules on the surface of EDA, structural characteristics of enlarged aggregates are partly determined by the structures of the original broken QED domains, SEDA and SSEDA. As mentioned earlier, due to quantum physical effects, even EDA composed of solvent molecules only, SEDA, have solute reminiscent structures. Therefore, due to epitaxial adsorption processes, even enlarged SEDA have solute reminiscent structures. Enlarged EDA have solute reminiscent structures. The next two slides illustrate the memory of succussive diluted liquids. Memory of condensed matter. Information can be stored in condensed matter by inducing some specific order. For example, certain memory devices, for example MP3, contain particles with magnetic moments. Whenever the magnetic poles of the particles are randomly oriented, the information content of the device is zero. Information is zero. Storing of information is done by orientation ordering of some of the magnetic moments. Storing of information. Information is not zero. Memory devices can also be constructed from materials composed of particles with electric dipole moments. Information is zero. Storing of information is feasible by orientation ordering of the electric dipole moments of some particles. Storing of information. Information is not zero. Memory of polar liquids. As noted earlier, according to ES theory, in water and other polar liquids, all molecules and their electric dipole moments are oriented randomly. In other words, these liquids cannot have a memory. However, according to QED theory, dilute succussed polar liquids contain EDA. Hence, such liquids have memory capabilities. Information is contained in the ordering of the polar liquid molecules within EDA. Information can also be stored by specific orientation ordering of the electric dipole moments of some EDA. As noted earlier, due to quantum physical effects, SEDA have solute reminiscent structures. Therefore, the internal structure of SEDA and the orientation ordering of SEDA can function as memory devices for characteristics of the solute molecules which were present in the mother solution tincture. The next slide details the effect of dilution on liquids containing EDA. Impact of dilution on EDA solution. Unsuccussed polar liquid. Dilution reduces EDA concentration. As mentioned earlier, an EDA is an aggregate of molecules, that is, a kind of supermolecular solute particle. At very low concentrations, CD-rod form and solute particles locate within these coherent QED domains. EDA locate within CD-rod. The next slide details the importance of location of EDA within CD-rod. As noted earlier, the solvent molecules within CD-rod rotate coherently and do not collide. Solvent molecules not organized in QED coherent domains move completely randomly and do collide. EDA located outside CD-rod do collide with solvent molecules. Collisions with molecules alter the energy of EDA. In physics jargon, this is called thermal aggression. Collisions with molecules may change their structure, may cause their breakup, even can lead to their disintegration. EDA located in CD-ROT. EDA located within CD-ROT. Do not collide with the coherently rotating solvent molecules. Therefore, location of EDA in CD-ROT preserves their structural characteristics. Analyses of 4-year-long experimental observations indicate EDA last at least 4 years. EDA located in CD-ROT have very long lifetimes. As noted earlier, CD-ROT only persists in very dilute solutions. Therefore, EDA preservation requires their concentration is very low. In other words, after creation of EDA during succussions, preservation of their structural and energetic characteristics requires that the liquid is diluted. Alternative procedure for preparing homeopathic remedies. Homeopathic remedies are also prepared by a technique which, instead of succussions, forces the liquid to flow very fast through a pipe. From fluid dynamic theory, it is well known that whenever a liquid flows very fast through a pipe, friction between the liquid and the inner surface of the pipe creates whirlpools. The whirlpools induced by fast flows, just as succussion-induced whirlpools, may break up QED domains. In regard of the above, it is to be expected that liquids forced to flow fast through a pipe have properties similar to those of succussed liquids. Future research is required to verify this conjecture. The next slide summarizes the respective effects of succussions and dilutions on polar liquids. Summing up, impact of succussive dilution. Liquid containing QED domains of type CD-ROT or IPDS plasma, that is polar liquid or very dilute polar liquid solution. Succussing this liquid creates EDA. Dilution, unsuccussed polar liquid. Reduces EDA concentration. EDA locate in CD-ROT. EDA protected against destruction by colliding molecules. The next slide details the effect of repetition of succussive dilutions of polar liquids. Effect of repetition of succussive dilutions. During a succussion cycle, EDA break up into smaller EDA. On dilution, the number of SSEDA and SEDA decreases. In between succussions and dilutions, EDA grow. During the next succussion cycle, the grown EDA break up into smaller EDA. Repetition of succussive dilutions causes the number of EDA containing solute molecules, SSEDA, to diminish. The number of EDA containing solvent molecules only, SEDA, to stay about constant. In repetitive succussive diluted polar liquids, when the concentration of solutes falls below the Avogadro limit, SSEDA are not present, SEDA are present. The Avogadro limit denotes concentration of one solute particle in a 1 liter water. Characteristics of liquids which are due to presence of SEDA persist when these liquids are diluted below the Avogadro limit. Effect of succussive dilution parameters. Increasing duration or frequency of succussions. Multiplies aggregate breakup events, which leads to enhancement of EDA concentration, diminishment of average EDA size. Enhances rotational excitation of EDA. Whenever at each dilution step the degree of dilution is increased, for example, instead of centesimal, C is 100 times dilution, and M is 1000 times dilution is applied, the EDA concentration will be lowered. End part 4. Impact of succussive dilutions.